back.
Usually go to UDP.
Today we're going to be moving on to the sort of second half of the IP layer discussion to chapter 5, I think, on the control plane. A few announcements first. Project 3 is due tomorrow, as I'm sure you know. The midterm grades were released, and I have the exams here, so you can collect these after class or during office hours. And the next assignments will be posted soon, both homework and project. No, not yet. Okay. Any questions about the midterm before we move on, or anything? All right. So last time I talked about IP version 6 and forwarding, like in other words, the way that routers move packets along the network. I defined private networks as being different than public internet locations because the addresses of the private network are not accessible from the outside internet directly. Usually there's a connection between the private and public network through a NAT. I sort of introduced IP version 6, and the important thing here is that there are 128-bit addresses, so it allows many, many more addresses than the 32-bit IP version 6, and that allows basically everyone to have a public address if they want one. That's a big difference. But the main disadvantage of IP version 6 is that it adds 20 bytes of additional header overhead because those addresses are a lot longer, and it hasn't been universally adopted yet, partially for this reason and partially just because IP version 4 works pretty well for most people. I'm going to have a couple more slides today to clarify some IP version 6 issues, so I'll go to those in a second. The other thing I talked about was sort of like showing a model of a router, how if you kind of look inside the router, you have multiple queues for both inputs and outputs, and packets can be dropped in any one of those queues. So it could be either just certain inputs are dropping packets, certain outputs are dropping packets, but not all of them at the same time. And some packets can be prioritized over others using a scheme like weighted pair queuing, where if you have some rule for classifying packets, like based on the IP address or the ports or certain QoS fields in the header that were added by other routers, you can make sure that certain packets are dropped for other packets, and that gives different levels of service. And net neutrality is related to this, is about whether or not this mechanism should be used by internet service providers. We also saw in that sort of investigation of routers how modern routers actually process packets in parallel, and they have a high-speed switching fabric between inputs and outputs, which could be either a bus or a crossbar, and crossbar allows multiple simultaneous connections. They can be reconfigured, where the interconnect can be reconfigured to connect different inputs and outputs, but a bus just has like one electrical path that has to be shared by everyone connecting inputs and outputs, and that creates a bottleneck. Okay. Any questions about last lecture? So I had a couple questions last lecture that I didn't answer well that I'm going to answer now about interoperability of IP versions 6 and 4. So remember I showed this picture of tunneling, how IP version 6 routers can forward packets to another set of IP version 6 routers through some intermediary IP version 4 routers by using tunneling, which means that you take the packet that was bound for this location and you actually wrap it up, you add a header to it, which is an IP version 4 header that actually has a destination of some version 6 router on the other end that can accept that packet and unwrap it, and then is able to handle the IP version 6 packet inside, because these intermediate routers don't understand IP version 4 and aren't using IP version 4 addresses. So this showed how different IP version 6 routers can communicate using intermediary version 4, but it didn't answer all the questions that you might have. In particular, so I'm going to introduce the idea of a dual stack host in the next slide, but these routers here, in order to communicate both with version 6 routers and also with version 4 routers, they have to be what are called dual stack hosts, meaning that they have both IP version 4 addresses and version 6 addresses. And they can't just have one or the other and expect to talk with the entire internet. So the question last lecture that I didn't answer was, how do IP version 6 hosts talk to version 4 hosts. So if you're on like an ISP that's fancy and gives you a version 6 address, how do you communicate with everyone, most of the other people on the internet that don't have version 6 addresses? And the short answer is you can't, which is a little bit unexpected. IP version 6 is not actually built to be backward compatible with version 4. There are solutions that allow you to get connected, but they usually involve using both version 4 and version 6 at the same time. So in some sense, the version 4 hosts on the internet, those IP version 4 version 6, those version 6 hosts across the internet, they're not all directly connected with IP version 6, so they're kind of islands of IP addresses that can communicate with each other using IP version 6 with those longer addresses. But then to reach everyone on the internet, and even everyone on the internet using version 6, you have to get out of your island to another island using a tunnel, like I explained in the previous slide. But that, again, that's just 6 to 6 communication. If we're talking about communicating between version 4 and version 6, you actually need to use both versions of the protocol. So a dual stack host is a host that uses both IP version 4 and version 6. So he actually has an IP version 4 address and an IP version 6 address, so both a short address and a long address. When it wants to communicate with an old style IP version 4 address, it uses its own version 4 address, and it wants to communicate with version 6, it uses a version 6 address. So, for example, if your ISP supports IP version 6, it will be running both a standard DHCP server that gives out version 4 addresses. It'll also be running a DHCP v6 server that gives out IP version 6 addresses. And if your computer that you're connecting is running an operating system that supports IP version 6, then your computer will send out a DHCP request and also a DHCP version 6 request. So it'll get an old IP address, an old style IP address, and a new style IP address. And then depending on who you want to contact, you'll identify yourself either with the version 6 address or the version 4 address and use the corresponding header format. So far, does that make sense? It's kind of, and then the router that accepts your packets has to actually handle both version 4 and version 6, and it also has to be running dual stack. So in addition, so this DHCP request returns not just your address, but also like the IP address of the gateway, the subnet mask, the IP address of the DNS server. All those IP addresses are going to be either version 4 addresses for the DHCP or version 6 addresses for DHCP version 6. So your router will actually have 2 different IP addresses, depending on which version of the protocol you're using. Which I think leads to the next logical question is, how do I know whether to communicate with some server using version 4 or version 6? So I'm a dual stack host. I have the option to use either one of my 2 IP addresses, but I have to choose one when I'm communicating with an outside machine. So DNS kind of solves this problem for us. So if you want to communicate, if you want to download the google.com webpage, so normally you make a DNS request to look up www.google.com. There's a special kind of DNS request that's a DNS record. It's a quad A record, so AAAA, which lists IP version 6 addresses. So your client, if it knows it wants to use IP version 4, it'll just make a standard, it'll look for an A record for www.google.com. But if it wants to try using IP version 6, it can query for a quad A record for that same address. Okay. And if it doesn't know which to do, it'll query for both and see what comes back. And that'll tell it whether it could use IP version 6 or version 4. Okay? Questions about that? All right, so here's so ignoring what it says on the top for a second, here's a flow for a client that has both a DNS server and a server that it wants to communicate with. So if it's www.example.com, it actually makes 2 DNS requests, one looking up the A record and another one looking up the quad A record. So this is asking for an IP version 4 address. This is asking for an IP version 6 address. It gets 2 results because this server actually supports both versions of IP. So you'll see that the first one is a dotted quad style IP version 4 address, and you also down here you have an IP version 6 address. So you see the colons. So the client now has 2 IP addresses it could contact, and it can use one of 2 protocols, and it can make its own choice. So you might assume that it would use IP version 6. It would prefer to use IP version 6 because it's kind of newer and better, and it could do that. But there's an RFC here, it's called Happy Eyeballs dual stack recommendation, where, so it turns out that actually sometimes IP version 6 is slower because there might be tunneling involved. So in general, we don't want clients to use the newer protocol just because it's newer. If your client wants to get the best possible performance, there are some cases when it may actually want to use IP version 4. So the recommendation in this RFC is actually that you try to use both. Like you try to establish a connection. So there's a TCP handshake that happens in parallel to the 2 different IP addresses. I mean, those 2 IP addresses are the same server, so they end up going to the same place. But it might take longer for the IP version 6 packet to get there if it has to be tunneled, so it has to be encapsulated, unencapsulated, or whatever. Or it might be faster, we don't know. But if you send them both out in parallel, and then you complete the handshake in parallel, so the SYN ACK comes back, and whichever one, the client can then decide to proceed with whichever one comes back first and is ready first. So in this case, the IP version 6 socket replied with the SYN ACK before the version 4 one did. So actually at this point, the data starts flowing out on the version 6 socket, whereas on the version 4 socket, the client just sends an ACK, and then it sends a reset, which closes the connection. Okay, so it actually is finished with version 4 socket, and it's going to continue with version 6. All right, does that make sense? I just answered the question you asked last time. But
I would watch the video.
in one ear. Yeah, so the short answer is dual stack. You run both IP version 4 and version 6 at the same time. All right, so basically to summarize that whole picture, if you have 2 machines that are both using the same version of the protocol, obviously everything works fine, right? If you have version 6, a version 6 island that wants to communicate with version 6 somewhere else that has to go through a version 4 network, you can use tunneling. So stick the version 6 packet inside a version 4 packet. The other way around works as well. If you happen to have an IP version 4 packet that has to, for some reason, wants to go through a version 6 exclusive network, you can tunnel it. You can encapsulate that and tunnel that as well. But if you have an IP version 4 host that wants to communicate with an IP version 6 host, that's not actually possible directly. So what you'd have to do is use a dual stack configuration, so your client would want to be running both IP version 4 and version 6, have both of those options available, and it would choose to use version 6 in this case, because the DNS request for an A record would fail, but a quad A record for IP version 6 would return an IP address. And the same thing holds for communicating between 6 and 4. It's not directly possible. One or both of the 2 would have to be using a dual stack configuration to bring it to one of these states here. Okay? Yes?
So you said that IP version 6 has been like kind of slowly adopted for the last 25 years. Is it at the point where most IP addresses on the internet are IP version 6, or is it still like 50-50, but there's just more congestion on the internet now because you have to deal with all these different conversions?
Well, I'm not sure there's more congestion because of IP version 6. There's more complication. So I think that I was looking at a paper from 2017, so last year, that said that Google was reporting at that time, or sometime previous to that about 20% of the traffic they were getting was version 6. And obviously Google's like a pretty good system to be looking at those statistics for, because they get a wide range of clients connecting to them. I would imagine that like all the main backbones support IP version 6 at this point. But a lot of the clients, I think the edge has been slowest to adapt. Yeah. But yeah, this is an area of like active research. So like IP version 6, like I said, was invented 25 years ago, but people are still trying to figure out how to get people to adopt it. So like how to set up tunnels when necessary, for example. Yeah. So there's some references to what I just talked about. The other question I got was, how do you find an IP version 6 tunnel endpoint? So if you're running an IP version 6 island and you want to connect to some other IP version 6 address, that's not within your own domain, but somehow has to go through an IP version 4 tunnel? Like, how do you find that tunnel? How do you make it? The answer to that is various, and this is one of the areas where there's room for improvement, even at the current time. So research can improve these solutions. So one solution is, if you're a really big organization like a tier 1 ISP, you can find other big players to peer with. So you either have direct IP version 6 connections to others, or if you don't, and you know there's a big block of the IP version 6 internet that you want to reach, then you kind of get on the phone and call someone that you know who might be able to set up a tunnel for you, so that you can peer with them. Just like in the early lectures, I showed that map of the world, and I was like, okay, here are all these ISPs, and they want to get better connectivity. The same thing applies to IP version 6 in the present day. So you have different operators that have IP version 6 networks, which are smaller than the version 4 networks. And if they want to expand the scope and get better connectivity to all the different IP version 6 addresses, it's in their best interest to create tunnels with partners that can get them closer to different parts of the internet. Okay, but a more interesting answer to that question is, if you're a small organization like an individual and you want to connect to the IP version 6 internet, you can use what's called a tunnel broker. So basically, you can find an organization that's willing to sell you access to their tunnel or give you for free access to their tunnel endpoint. So for example, Hurricane Electric, which is a tier 1 ISP that you probably have never heard of, but is actually the biggest tier 1 ISP in the world, according to them. At least they have the most connections to other, they have the most peering connections of any other tier 1 ISP. I don't know if they have the most traffic, but they have the most connections. Anyway, if you go to this website, you can actually follow some instructions to set up your own personal tunnel to one of their servers. They have a lot all over the world. And they'll also give you a block of IP version 6 addresses. So even if your ISP doesn't support IP version 6, you can get started using IP version 6 using this Hurricane Electric tunnel. Yes?
How does, when a datagram's passing between different routers, how does it know to unpack, say that it's IPv6 inside an IPv4 datagram?
Yeah.
How does that router know that? Is there a bit that's set to indicate that?
Yeah, there is. So I don't have the slide in this deck, but in the previous deck, if you look at the IP version 4 headers, there was somewhere in the IP version 4 headers. So you have you have a lot of different fields in here. This is a IP header. Somewhere there's a type, which is usually either TCP or UDP. There's a 8-bit number, I think. But so the receiver has to know how to interpret this down here, because both TCP and UDP have different formats for what is in the header. And so what this is and all these other fields has to be known. And the way you know is by checking this type field. This can also be IP version 4 or IP version 6 to indicate that what's down here is another IP packet that's encapsulated in a larger IP packet. And there's some other connections involved. Okay? All right. Right, so that's kind of leaving our discussion of the IP data plane and addressing and forwarding, kind of the low-level details. The next topic is the control plane of IP, which is how we decide the forwarding rules at each of the routers. So this is concerned with what we already talked about was the nitty-gritty details of how packets get from one hop to the next, but this is the logic that defines how packets get through an entire path, how the paths overall are decided. Okay. So we have algorithms that do this, that somehow decide all the rules at all the different routers. And there are different types, so we'll talk in the next lecture about the specific protocols, but this lecture is more about the principles and surest path algorithms in general. But they're both global and distributed algorithms. So when I say global, I mean algorithms that operate globally on the whole problem at once, and another word for that would be centralized. So a centralized routing algorithm would have full knowledge of the entire network, would know where all the routers are, what the links all look like, and what the traffic maybe looks like, and would make a decision that affects all the routers. And that's kind of the first logical way you would probably approach this, because the simplest way to solve the problem is to have all the information, right? If you want to truly get the shortest paths from end to end all across the whole system, it makes sense that you would want to know all the information about the whole system. We call these link state algorithms because they require that you know the link states, meaning like what are all the links in the whole network, and how fast are they, or how much capacity do they have, and whatnot. And these are used in cases when you do have all that information. So to figure out what the optimal routing is within a single organization, which is called an autonomous system, we'll talk more about what this really means in the next lecture, an autonomous system. But you can think about it as a network that's controlled by one organization. There are protocols like OSPF that implement these centralized routing algorithms to come up with solutions for the shortest path when you have all the information. Okay? That's one class. And then the other class is what's used over the entire internet, because the internet is not controlled by one single organization, it's a bunch of cooperating decentralized systems. And in this case, somehow each router or each autonomous system, actually in reality, has to decide its own routing table using just local information without getting the information from the entire world. Because there's too much information, there's not sharing of information, you can't trust information that's shared. All you know is what you see locally. And these algorithms operate iteratively, meaning that as time goes by, more information is gained, and information changes, and routes are adjusted accordingly. And this is what's used in like BGP, which is the famous border gateway protocol that kind of connects the whole internet, which we'll talk more about in the next lecture. But to implement a decentralized routing algorithm, routers have to share information with their neighbors, but they only communicate with their neighbors. They don't get the information about the entire worldwide network from their neighbors. They just get some kind of summarized local information from their neighbors. And they're sort of constantly getting information from neighbors, providing information to neighbors, but only acting locally. And this is used to decide the routing within but mostly between autonomous systems, which is to say, if you're an organization operating a network, you have several neighboring organizations, you want to know which traffic should go to which neighboring organization, or autonomous system in this case. That's what they're called.
What are those names of the example? Is it just names of companies?
So these here are protocols. Is that what you're asking? Yeah. So BGP, Border Gateway Protocol, is a standard protocol for determining routing between autonomous systems. So kind of large-scale routing in the internet. And we'll talk about that later in detail. OSPF is Open Shortest Path First algorithm protocol, which is a protocol for, I think it was developed by Cisco for determining routing tables within an organization where they're all cooperating. And RIP routing something protocol, interchange maybe, I don't know. This is an older one that is actually also intended to be used within an organization, but it's distributed. Yeah, question?
Is that saying within ISPs they use centralized and like between ISPs they use decentralized?
Kind of, that's how you can think of it. But autonomous systems or organizations are more than just ISPs. They're also like large companies, like Northwestern University is an autonomous system that maintains a series of routers. I mean, it also is an access network for the students here. So it's an ISP in some sense, but it's an autonomous system generally. Okay, so to study this problem of routing, we're going to be using a graph abstraction of computer networks, which I'm sure some of you have seen, maybe some of you have not. So we'll talk about, this lecture will kind of cover that and the different algorithms that work for these graphs. And particularly, we want to solve shortest path algorithms on graphs. Okay, so a graph in the sort of computer science discrete math combinatoric sense is a set of vertices and edges, and you draw it out like this. So it's a bunch of dots and lines connecting them, and the dots are vertices, and the vertices in this case represent routers. And the edges connect routers or vertices, and the edges have different weights, which somehow represents the cost or the distance, latency of using that edge. So this link here that says 5 is somehow a longer link than this one that says 2, right? And overall, what we're trying to solve is, so these edges represent the distance or cost to communicate, which is generally latency. So we represent vertices by letters in these slides, and edges are pairs of letters. So XA means that you have an edge that connects X and A, so this is that edge. And there's a cost for these edges, which is represented by C, and then the two vertices that are connected. So C, XA, like this, is the cost is equal to 2, and that's the picture shows 2 there. And you also have some nodes that are not connected at all, like Y and B are not connected directly by edges. If you want to, in some models, you might still say there's an edge there, but the cost is infinity. So you can't. So like logically they're connected, but the cost to travel that route is like infinite. Same thing. Whether you leave it out or include it and give it a cost. Okay. So, like I said, for now we're going to assume the cost is the delay. We're going to ignore capacity, and actually most of these algorithms do ignore capacity, interestingly, which is kind of counterintuitive. But we also know that from our study of routers that if a router has too much traffic, either in its links or kind of in its in terms of its internal processing capacity, then it will start to have longer queuing delays and so on. So actually, capacity constraints tend to turn into delays anyway. So this model is pretty good. So we want to know what's the shortest path we can send a packet along to get to a destination. All right. So like I said, it's a shortest path problem. A path is defined as a series of edges that are connected by intermediate vertices, of course. And so we're given this graph. It's a weighted graph, so there are numbers associated with the edges. We're also given a starting vertex and a destination vertex. In this example, the starting vertex is X, and the destination is Y. I'm trying to get from X to Y. And generally, there's an optimal solution. There could be multiple optimal solutions with the same cost going through different paths. And this is a solvable problem in polynomial time. It's not a hard problem in the sort of computer science sense. Yeah. So we want to know both the path and the total cost when we're coming up with a solution. So in this particular example, the shortest path happens to be here along the bottom from X to B to D to Y. And the total cost is 4 because we just add up the edges 1, 1, and 2 gives 4. Note that if we tried a very simple algorithm to solve this problem, like a greedy algorithm that just that always chose the shortest path, shortest edge that you have available, then you would end up with a bad solution. So if you chose 1 because that's short, then maybe you chose 1 here because that's shortest of these. Then at this point, you might choose 1 because it's shorter than all the other options here. And then you might choose 3 because it's shorter than the 5, and so on. So like a really simplistic algorithm won't work. But like I said before, this isn't a really hard problem. It is solvable in polynomial time, but we have to come up with some good solutions. In reality, using dynamic programming, it turns out. Okay, so how many of you have taken 336 or the equivalent, like an algorithms course? How many of you have not taken 336 or an algorithms course? Okay, so it's like half and half, maybe more that have not taken it. I think that would be the place where you would see something like this, unless you happen to take a graph theory course or something, which would be less common. So, solve this problem efficiently. It turns out that we want to break down this problem into subproblems, which is the key idea behind dynamic programming, which you would learn in 336. So here you'll get a little flavor of that if you haven't seen it, or it'll be a review of it if you have seen it. So what I mean by subproblems is that if we want to solve the shortest path from X to Y, but in order to do that, we solve other shortest path problems. And those kind of build on each other to get the final solution in an efficient way. So in general, so if we just look at this, the shortest path from X to Y, in this particular case, we know that if we kind of look backward, it's one of two things. It's either the shortest path to C plus 5, or it's the shortest path to D plus 2. Okay, because we know that to get to Y, we have to pass through either C or D, one of the neighbors, and then to get from that neighbor to Y, we would use the link that's available, which has the cost that I said. But then to get from the beginning to that second to last place, we want the shortest path, obviously, right? If overall we're going to get a shortest path. So that's an important observation, because that's a subproblem. And we know that eventually we can get to the point where we know that the small subproblems are very easy to solve. Like the shortest path from X to X is trivial, it's just going nowhere. The shortest path from X to B is also trivial because it's just one hop. The shortest path from X to A is trivial because it's one hop. The shortest path from X to C is trivial, is actually maybe not trivial because this is actually the shortest path. But yeah, the shortest path of it turns out of length 1 is trivial to solve, which is a different subproblem. Anyway, so I'll come back to that later. But yeah, we have to use subproblems. So in particular, what I was just describing is that the shortest path, XY path, has a final stop of either C and D, and then we can calculate the cost of using that final stop and figure out which one of the two options has the minimum total cost. Okay. So the two parts of that subproblem are the cost of the path that almost gets there plus the cost of the final step. All right, so formally, that turns into what's called the Bellman-Ford equation, which is the basis of, I think, all the different shortest path algorithms. There's one called the Bellman-Ford algorithm, and then there's also Dijkstra's algorithm. But Bellman-Ford equation and Bellman-Ford algorithm are two different things. Anyway, so this is like, I think, one of the earliest proposed efficient solutions. Actually, no, sorry. This is the basis for the Bellman-Ford algorithm, which was one of the earlier solutions to this problem. Okay, so basically what we can say is for any pair of nodes in this graph, we can represent the distance from the first node to that second node as being it's 0 if the two nodes are the same, okay, it's trivial, or it's the minimum among all the possible previous steps. Which is, this is just formalizing the specific example I had before, had only 2 previous steps, but this is taking the same minimum over, in general, all possible v's, which are neighbors of y. Yeah. So the shortest path between x and y must pass through some vertex v that is adjacent to y before finally arriving at y. You consider all those different v's. You take the shortest path distance to that v plus the cost of going from v to the final y, and whichever has the shortest sum of those two factors is your shortest path solution overall. And then we kind of build up the solutions from the beginning. So to actually calculate this, we have to consider every possible v neighbor of y that we can pass through. One of them has to be the right choice because we know that the path that gets to the finish has to go through some neighbor of the finishing node to get there. And if we somehow assume we've already computed the cost of the subproblems, then we can come up with a solution. And this is a recursive solution. In order to do this efficiently, we have to structure the subproblems so they can be built from small to large without doing a lot of work, basically. And so the way this is done in the most simple way is with the Bellman-Ford algorithm. Sorry, the grays are a little bit light here. But so we start, I'm going to show you two different algorithms. One is the Bellman-Ford algorithm, one is Dijkstra's algorithm. They both build up subproblems using the Bellman-Ford equation, but they do it in a different way. And what's different about them is the invariant. So this is actually like the most important part of it. Once you understand this, then the code is trivial. But with the Bellman-Ford algorithm, you go through rounds. So you have I different rounds. And in every round, you're calculating the shortest path to every other node using at most I hops. I hop, yeah. That's true. So like at first you have 0 hops that are available, right? And you know that you can't get anywhere with 0 hops. So so the next round is 1 hop, and using 1 hop you can compute. You can take all the solutions to the previous problem. So the subproblems we have in this case are essentially so actually, I probably should have written this in a slightly different way, that where it was parameterized in terms of both the round and the destination. But distance ij has I is the number of hops, and this is the destination, and this is the shortest path that we know of. This actually is the true shortest path using a certain number of hops to get to a certain destination. And this can be expressed recursively using I minus 1 hops plus 1 additional hop that you're considering around. Okay, so you initialize the vertices. So initially, you have this distance vector that is for the current round. For the current round represents the number of hops. What's the distance to each of the nodes? Initially, it's infinity because you don't know of any way to get anywhere. And except for one case, the source itself. So you know that you can get from the source to itself. By source, I mean that first node. To get to the first node, you can get from the first node to the first node in 0 hops in 0 distance. That's what this initialization is. And then the meat of it here is just considering all the different rounds. And like I said, at round I, you're computing the solutions for at most I hops. So starting off with 1 hop, and you stop when you get to the size of the vertex set, because you know that the shortest path is never going to have more hops than the number of vertices, because at most you can only pass through every vertex once. You would never visit the vertex twice in the shortest path, because that means there was a loop that you could circumvent. So so you do what's called a relaxation of every edge in every round. So basically, you consider every edge in that round, and you ask yourself, does that edge create a new shortest path? So yeah, I can't do that. So basically, so every edge in this ith round creates an alternative route, which is the cost so this is from the previous round. The distance to get to the source to one end of the edge, plus the cost of getting from the one end of the edge to the other end of the edge. This gives you in total. So previously we could get to. Sorry, we're considering an edge. Considering an edge UV, which means that we have a node U and a node B, and there's an edge here, and it has some cost, CUV, and this is somewhere in the graph. We don't know exactly where it is, but somehow this might help us get from the source X to destination Y. And what we do is, in that test here, we say that we might be able to use this edge to get to V in a shorter distance if the path to U from the previous round plus the cost of this edge. So in other words, I minus 1 steps go to U, and then 1 more goes to V. That's this plus this. If that's less than what we had in the previous round, I minus 1 steps to go to V, then we use that as the shortest path. We say that that is the new shortest path to get to V. Yeah. So if that alternative is shorter than what you've had previously, then you redefine the shortest distance to be as being that alternative path, and you just keep track of this previous vector, just keeps track of the previous node in the steps in the path so that you can trace it back at the end when you have a final solution. But eventually, after I rounds, this will get the optimal solution for all the nodes. Yeah. Okay. So,
I being the number of vertices.
yeah, because in every round, this distance vector, dist, is always storing the shortest path to get to all the different nodes with at most I hops, I being the number, the round number. So after initially it's 0, and the only one you know how to get to in 0 hops is the source node itself. You can get to it in cost 0. But then subsequently in every round, you consider all the different edges and see whether that edge will get you to another round and another node in less distance than you already had noted in the previous round. So I guess just to make it a little bit more clear, if we have this is the source, this is the destination. So I'm going to mark. Let's make this a little shorter. Okay, so those numbers represent the edge costs. So initially, first round, so when we start off, all we know is that the cost to get from S to S is, let's say, is 0. So we have a 0 here, but then for all these other ones, we have infinity, and so on. Because with 0 hops, we can only get, we can't get to any of the distance to. If we only have 0 hop, 0 length paths to use, the distance from the source to everywhere is infinity, except the distance from the source to itself. When we move to round 1, we consider all the edges, and we check both endpoints of the edge to see whether we get any better. So for example, if we started off with this edge here, we would say, okay, can I use this edge to make the distance to here shorter than it was before? So previously it was infinity to get here. If we add 2 to infinity, we still get infinity here, so we cannot. So the answer is no, there's no change in the first iteration using this edge. Same thing for all these other edges. But when we consider these 2 edges, we will get a different result. So if we try to relax the distances using this edge 2, so we came to this one first, we would say that, like for this node here, the distance is the alternative provided by this edge is like 0 plus 2 equals 2, which is less than infinity, which we currently have stored there. So we actually update this to 2 because we know that there's a length 1 path that gets here in cost 2. And then later we would consider this edge, which is actually a little bit shorter, and we would do the same thing and actually end up with 0 plus 1 equals 1, which is less than 2, which leads to a new cost of 1. Oh, sorry, no, that's not for this one. Sorry, that's bogus. When we consider this edge, it would be the same thing for infinity. So it would be 0 plus 1 is less than infinity, leading to a cost of 1 for this one. So basically, after one round, for considering all these edges, the only changes we would get would be that these 2 nodes would now have numbers less than infinity for their distances. And we can repeat that for all the different lengths of paths until eventually we end up with some paths that lead to the destination. And they won't necessarily be the optimal paths, the optimal distance to get to the destination until we do like the number of vertex rounds. So like 1, 2, 3, 4, 5, 6, 7, 8. Until we do 8 rounds, like I equals 8, only at that point will we have the optimal for the final destination. Questions about that? Okay. So that's efficient. The runtime complexity is the size of the vertex set times the size of the edge set. Pretty easy to calculate because this loop goes through the number of vertices. This loop considers each edge each time. So you just multiply the 2 to get the number of operations. There's a faster algorithm called Dijkstra's algorithm, which it uses the same principle of relaxation, which is to say you look at an edge and see whether it provides a new shortest path to the other end of the edge, but it uses a different invariant, so it basically builds up subproblems differently. So specifically, so the rounds are different, in other words. Instead of saying in a previous algorithm, Bellman 4 algorithm, the rounds were gradually making the paths longer. In Dijkstra's algorithm, the paths are gradually visiting more nodes. Okay, so the invariant is that at a given round, we have a set of nodes that were visited and those that were not visited. And the shortest paths that we have recorded at a given time is the shortest path using only those visited nodes. But if you need to include some other nodes that haven't been visited, then unvisited nodes may provide a shorter path. But if we're just using those visited nodes, we have the shortest path so far. So we initialize it in almost the same way, but then we maintain a set of visited nodes, which is Q. Unvisited nodes, Q. And this loop goes through each vertex. So every iteration is considering a new vertex, considering visiting a new vertex. And we visit the vertex that has the minimum distance from the source so far. And then we look at all the neighbors of that vertex to try to make shortest paths to those neighbors. And if we find one, then we record it, otherwise we don't. So doing the same kind of test of whether we can get from this currently visited node to plus one of the edges from that node elsewhere. Does that provide us a new shortest path? And if so, we record it, otherwise we don't. So we can use that same algorithm here. Well, let's actually make sure that we know this. The initialization is the same. The only thing that's going to change is the way that we add new information. Yeah. So, I guess this demo is a little bit sloppy, but hopefully the explanation helps. So we start off here, again, all we know is that we can get from the source to itself in 0 hops. Now, we start off with, we want to visit a node. The node we decide to visit is the one that's closest to the source. In this case, there's only one that's closer than others to the source, which is the source itself. So we visit the source node first, and I'm going to mark that with a color, make it blue. So let's say blue equals visited. And when we visit it, we consider all of the edges that go out from it. So we look at this edge and we say, can we contract this to get a new shorter distance? Meaning, can we take the source distance, add it to the edge, and get a shorter distance for the destination? The answer is yes. This gives us 2 here. Can we contract with this one? Yes, this gives us 1 here. And then we're done with the round. The rounds are actually shorter because they just consider the edges associated with with the new visited vertex, they don't consider all the edges. That's one of the reasons why this is more efficient. So now, next round, in the next round, we have to consider the, we pick out the vertex in the set of unvisited vertexes, which has the shortest distance from the source so far. So that would be this one here that has 1 distance that's shorter than 2, which is shorter than all the infinities. And then we consider all the outbound edges from here. So there's just 2 of them. And so 1 plus 1 gives 2 to get from the new visited vertex to S. 2 is greater than 0, so it doesn't change anything. But 1 plus, if you look at this edge, 1 plus 2 is 3, which is greater than the infinity that's currently stored for that edge. So I'm going to change this one now. This node here can be visited in 3 after visiting this node, right? So that that's all that happens after that round. And then we repeat it. Now, now we get to visit another node. We choose to visit the one that's closest, that hasn't been visited, which is which one? 2, up here. We visit this one. And this edge here doesn't help because it gives us a distance of 4 to get to the source where previously we had 0. This edge does help because we can do 2 plus 2 equals 4, which is less than infinity that we previously had. So we get 4 for this one, and that's how we proceed. So we would visit this one next, and so on and so forth. And that would eventually give us the optimal solutions to the distances to all of the different nodes. Okay. I guess so far it's not. I haven't proven that this gives the right answer. But I'm not sure if I'm going to do that. But let's look at the runtime first. So we saw the previous one was the number of vertices times the number of edges. In this Dijkstra's algorithm, there are 2 different versions. So the simpler version is actually v squared, the number of vertices times the number of vertices, which is better than the number of vertices times the number of edges, because the number of edges is always greater than the number of vertices, generally, because every vertex can have multiple edges. So this is better. The way you get this is saying that, okay, this outer loop goes at most v times, because it tries to visit each node. And then when we consider the neighbors, all right, so no. When we when we look for the minimum, when we look for the vertex that has a minimum distance, we have to kind of scan through at most v possibilities to find the minimum one. And so that is this operation here actually takes v steps. Down here we have a very small number of iterations, at most in aggregate, the number of edges. But that's an inefficient solution. We can actually, if we organize these distances inside of a data structure, like a priority queue, we can, in log n steps, get the minimum. And that's what turns the real runtime into v log v, which is v is the number of iterations here, log v is the cost of doing this lookup. Or either the shorter of either that or the number of edges, because we know that we're going to consider contracting every edge twice, once for each side of it. But this isn't too important for this class, I guess. So understanding how it operates is more important because you're going to be implementing both this algorithm and another one in Project 3. Okay, maybe I should have said that earlier, so you pay attention to my explanation. You have to do this algorithm, so you have to know how it works. Yeah, sorry, that's a rookie mistake on my part, not telling you that ahead of time. Okay, so here's an illustration of Dijkstra's algorithm in action, starting off down here. It visited this one, visited that one, and now it's visiting nodes that are next closest based on what it currently knows. And then this blue tree is showing the current shortest path tree that was built. And this graph is arranged such that there aren't numbers on these edges because the actual distance is the actual physical distance in the drawing. And so it kind of does a breadth first search in some sense over the distances. The next one, so it's visiting this one right now, visiting this one, and the ones that it visits are gradually further and further away from the source. And yeah, so the invariant, the thing that's always true is that using the visited nodes, which is to say the ones that are connected by blue, we know the shortest paths everywhere, assuming we can only use these visited nodes. We don't have a shortest path to here yet because we haven't visited enough nodes, but now we have. Yeah, so I did that out example. All right, so comparing those two algorithms that I showed, one's faster, one's simpler. Basically, that's what it comes down to. Bellman-Ford is simpler, and because it's simpler, it can be adapted into a distributed implementation called the distance vector algorithm, which is the second. So you'll be implementing, in Project 3, you'll be implementing Bellman-Ford in a distributed fashion with distance vector, and you'll be implementing Dijkstra's algorithm in a centralized fashion where you have all the information. And so the terminology the book uses for these two different styles is that the distributed algorithm that happens to use the Bellman-Ford, a variation of the Bellman-Ford algorithm, is called the distance vector algorithm. I'll talk more about the details of that because it's not exactly what I showed you. And this is kind of what BGP does, in a way, between different autonomous systems. So this distributed distance vector algorithm, based on the contractions like I showed you, is what BGP does to figure out the routes across the entire internet and recover from failures and all that kind of stuff. Dijkstra's algorithm is this fast solution to the problem where we have all the information. This is used for algorithms like OSPF that are centralized, and the book calls these link state algorithms, like I said, because they require that you know the state of all the links. So in some cases, one's better. In some cases, the other is better. It depends on basically whether or not you have the ability to implement things centrally. You have information on the entire graph. So the distance vector algorithm is a variation of the Bellman-Ford algorithm. It's not exactly it. It's actually it's more complicated because it's distributed. So every vertex, which is in reality a router or node, maintains a distance vector, which is an estimate of the shortest path from myself to every other point in the network. So this is kind of like your current best solution to this shortest path problem. How do I get from me to everywhere else? This is what you need to know in order to route. So if I want to send a packet somewhere, I want to know what the shortest path is to get to the destination. And that tells me which link to choose. And this D of Y sub x is like the router that is storing this, tells me what the shortest paths are. But every node has its own distance vector, but it also stores distance vectors from its neighbors. So in general, you have, does this notation make sense? Distance vector node. Yeah, so, sorry, so this notation here is for a single destination. To get from me to a destination, to get from x to y, d sub x of y is a single number, and then the vector is capital D sub x, which has those numbers for all the different destinations, but still from myself to everywhere else. So it's like a bunch of distances to other locations. And you have to calculate that. You don't know it ahead of time. What you do know is the cost to reach all your neighbors, V. So this is like just, if you look back at the example, like this node here knows the cost of these edges surrounding it, these three. Doesn't know anything else, it just knows what's going on locally. Okay? So that information has to be shared, and the algorithm that computes the shortest path has to somehow converge to a solution as more information is shared. So the way it works is that it's a series of rounds where people send their latest distance vector to their neighbor, and their neighbor tries to do a contraction to see whether they can come up with a better solution to their own distance vector, and if they do get a better solution, they share that with all their neighbors. and it just continues infinitely until eventually, if nothing changes, you don't tell your neighbors if that anything is, you don't broadcast a new distance vector to your neighbor, and so eventually it converges. So you start off by sending your own distance vector to your neighbors. That's based on just the local costs that you know. At first, all you know is what the distance is to your neighbors. You don't know about multiple hops yet. And you also keep a copy of the distance vectors that were received from all your neighbors. So basically, the information that your neighbors have given you about how they can reach others, you need to save that. You only need to save the latest copy because they're going to tell you, they're going to give you new information over time as their information gets more accurate. So you keep a copy of all the recent advertisements from your neighbors. You use that to update your own information. You recalculate your own distance vector when you get new information from a neighbor, and if it's changed, then you broadcast it, and this kind of iterates. And eventually converges, and every node knows the shortest path to every other node. Okay. So the distance vector is recalculated using the Dolman-Ford equation to do contractions. So it's the same formula of taking the distance to get to a certain point plus the cost that you know to get from that point to another point, and seeing whether that total cost, path cost, is less than what you previously thought was the cost to get to the destination. Okay, so initially all you know is you have a vector that just contains the observed costs from nearby edges. Like, you know what the latency is to your neighbors, so you use that to say that the cost to get to my neighbors is a certain amount. It's infinity everywhere else if you don't have direct links. You're going to hope to fill in that information later as your neighbors tell you, oh, actually I can get to this destination in 5 milliseconds. So that you can infer personally from that that I can send a packet to that neighbor, and then the time it'll take to get to the destination is that 5 seconds plus whatever delay there is between me and the neighbor. So we look through, every time we get there are two things that can, I'm not sure, do I have unfortunately I guess I don't have I have these two slides that describe it, but it's kind of wordy and not like algorithm-y. So I think, but if you read it a few times, I think it'll make sense. There are two different actions that cause you to update your distance vector. Either you get a new distance vector from your neighbor, or you get a new cost for a local link. So in other words, you observe that a link locally has gotten slower or faster. Because both of those different things feed into your current calculation for your distance vector. So every time you get new information, you just go through all the different possible destinations. You calculate the new shortest path to every destination by saying the cost, it's the minimum among all the different possibilities. Basically, you look at all your neighbors, the cost to reach that neighbor, plus the distance that that neighbor advertises to get from himself to the final destination. That's your candidate if you choose that node as the next hop for the resisted destination.
This is kind of an aside, but I'm wondering how it's secured, because theoretically, can't you take all the traffic from a network if you just keep broadcasting that I'm the closest node to you?
Yeah, so far there's no security built in that I described. What would happen? If a neighbor makes malicious advertisements, I think you need some other mechanism to monitor that and discover that and stop listening to advertisements from that person. Yeah. This is actually assuming a degree of trust, I guess. But I guess you can also, it's not too hard to do some monitoring of traffic going in a certain direction to see whether the actual observed round trip times, I mean, you have to do something different than what a typical router does, which is just forward packets. Usually routers don't look at, like, for example, TCP ACKs and match them up to initial sequence numbers in the other direction to figure out what the round trip time was. But the router could do that to get empirical information to validate or invalidate different routes. Yeah. I'll see if I can come up with a more better answer to that next time. All right, so basically every node goes through this loop. It waits for changes in local link costs or for an updated distance vector from a neighbor, and then it recalculates the current distance vector based on all the neighbor's distance vector and its own costs, and then it sends out a new distance vector to the neighbors if its distance vector has changed. So if it has a new distance vector, it broadcasts it to its neighbors, and then the neighbors are doing the same thing, so then they will see it and update their own information. Yes.
So to clarify, every router would actually have a distance estimate for every other router in the network? That seems like a lot, no?
Yeah, so in reality, the nodes in this graph for like BGP are autonomous systems, and yeah, you'd have a graph of tens of thousands of nodes, something like that. I'll check on that. So when we talk about destinations, we're not talking about IP addresses. We're talking about whole network chunks. And all right, so I might clarify that next time. So if we're using a distributed algorithm to solve the same shortest path problem here, it's a lot more complicated because it's not one algorithm. It's like it's a single algorithm that's happening in parallel on a lot of different nodes. So let's actually use a simpler topology as an example. So if we have like A and B and C and D, I guess. Yeah, this will fit. They're each running this distributed algorithm. They each have their own distance vector, and they each have copies of distance vectors they receive from neighbors. So if we look, we're going to show the code or the operation for this node A. So initially, the distance vector of A is, I'm assuming that I'm going to use indexes that correspond to the alphabetical position of the letters. So I guess I got to draw this first, otherwise it doesn't make sense. That's the graph. So A to A is 0, A to B is 1, A to C is 1, A to D is infinity. Okay, right now I'm assuming that the cost of all the edges is always 1. So let's actually throw out the weighted graph assumption. Just for a moment. Okay. So does this make sense, this initial distance vector? And then the distance vector for the algorithm running at B, it will have 1, 0, 1, 1 as its distance vector. It can actually reach, even from the start, it can reach every destination because it has observed these 3 links. It knows that it reaches these other 3 neighbors, and that's great. So, but A doesn't have that information yet, nor does A have any other distance vectors. So when the algorithm starts, everyone will broadcast their distance vectors to their immediate neighbors. So this B will be received by A, and eventually A will also receive DC. Well, let's say that won't happen until later. I mean, it has happened in some order. Let's say that B is received first before C. When that happens, now A has 2 distance vectors. It has its own, it has its neighbors. and it doesn't have any for these other two neighbors. Actually, this D is never going to be a neighbor. It doesn't have C's yet. So I guess if it hasn't received anything yet, we might say that it has a maybe an implicit, has no knowledge, so it thinks that it's infinity, but we'll leave that off. So what A will do is it'll recalculate its distance vector using all of its neighbors. So it gets dA prime, which is the new one, which is going to be, it's either going to be the old value or a neighbor's value plus the cost to reach that neighbor, whichever one is lower. So for the first position, it previously had 0. It can't do any better than that, so it's going to get 0 again. For the second one, it had 1. Its neighbor had 0, which is pretty good. But in order to use that 0, it has to actually include this 1. So 1 plus 0 is 1 again, so it doesn't change. It's still 1. To get to C, it previously had 1. The neighbor said 1. 1 is so to use this neighbor's route, it would have to travel to B first. So in other words, for all of these distances that are advertised by B, so B is advertising the length of these routes. If A wants to make use of these, it has to add this 1 to it, because it's going to go 1 hop to B plus whatever is listed by B. Okay? So for the C position, the alternative provided by B is 1 plus 1 is 2, which is less than the 1 that we already have, so we're going to keep the 1. But for this final position, for D, the best we know so far is infinity, and B is advertising 1. 1 plus 1 is 2, which is better than the infinity we had before. So after that first round, the distance vector for A is 0, 1, 1, 2. And then there also would be, in addition to the distances, you would also notate what the next hop was, so that you can actually use that for routing purposes. So the next hop for these other ones was actually all A. It was like, sorry. It was A, and B. We only used B for one of them. So this is now the new information that is stored by A, and this tells it that to reach these 3 locations, A, B, and C, it can use itself plus, I guess, plus the length. But to get to D, it can use B as the next hop, and the distance will be 2. Okay. And then now that it has this new distance vector, A will advertise that to its neighbors, and that will cause both B and A to recalculate their own distance vectors. Okay?
How do you know when to stop updating the distance vector?
You don't. Oh,
Do
okay.
you just
So
wait until it converges?
you don't know that it converges. What you do is let me bring up the slide. I have this in the slide, I think. You notify your neighbor if your distance vector has changed, and you wait until there's a new distance vector that's received. So when you do this recalculation, if nothing has changed, you're not going to broadcast anything. If you don't broadcast anything, then your neighbors are not going to receive anything, and therefore your neighbors won't do anything new, and therefore they won't do any calculation, they won't do any broadcasting. So eventually, when things stop changing, new messages stop being sent, and recalculations stop happening. Okay? Then the thing that would cause it to change would be if a local link cost changes. Yeah. So I used all ones in this example, but if it went from, if one of these links went from 1 to 2 or something, then a node would notice that, and it would have to recalculate its current distance vector using that new value, and that would cause a change, and then there'd be a broadcast. Yeah, which is what it's saying here. So in the example, this example here, simple like 3-part graph. If this node goes from, if this edge goes from cost 4 to 1, then both of these X and Y routers would recalculate their distance vector and notify their neighbors. And then they would send, and then the neighbors would then tell their neighbors about the new information and so on. But so one of the sayings we have here is that good news travels quickly and bad news travels slowly in these networks. So that'll become clear when we look at the bad news case. This is a good news case because a link became faster. When we say bad news travels slowly, that means that if you have an edge that goes from, say, 4 to 60, in this case, it'll actually take 44 iterations for this algorithm to reconverge in the correct solution. Because there will be what's called a count to infinity problem. So what happens is this node here, it thinks that it can still, if it still has the old distance vector from its neighbor here, previously this node y, for example, thought that it could get to x in 4 steps and to z in 1 step. After this goes up to 60, the correct cost from y to x is actually 51 here. But if x still has that old information of 4, it'll still use it, and it'll potentially use, they'll think that it can send, I have the example mixed up. Basically, because it's using old neighbor information, and the neighbors are also using information based on the neighbor, they'll slowly increase their distances until they finally reach the correct solution. I'll show an example of that next time, I guess, because I'm out of time. But to kind of summarize these two approaches, the centralized algorithm is more efficient. The distributed algorithm is nice because it can work without, just based on local information. But it's hard to know how long it'll take to converge. And there's a count to infinity problem, which I was trying to mention that last slide. I didn't really get enough time to explain it. All right. So overall, what we talked about today was, first of all, just talking about how IP version 6 and 4 require a dual stack configuration really to let nodes communicate everywhere in the internet. And we started talking about routing algorithms, which are basically solutions to shortest path problems on graphs. We showed Dexter's algorithm, which was fast and centralized, and the Bellman-Ford algorithm, which was less fast, but then we kind of adapted it to a distance vector algorithm, which can be distributed. And distance vector algorithm is used in BGP, or gateway protocols we'll talk about next lecture. And Dexter's algorithm is used in some protocols that operate within a network that's controlled by one organization. Okay? And one interesting thing about this is that the reason you can use Dexter's algorithm is that if you're in a network that's small enough that all the routers can broadcast all their information to everyone else, and if you have enough space to store that information, then you can do that, right? So the way that you can actually use a centralized algorithm in a router network is that all the routers first broadcast their information to everyone, and once everyone has all that information, then they each can solve the problem locally. And they each will come to the same solution, but first they had to broadcast their information. And then in Project 3, when you implement this, the most tricky thing is implementing this flood or broadcast of the link state information. All right, so that's it. If you want to collect your exams, I have them. We can come to office hours to do that as well.